Okay, and I want to talk about and recap the content of our uh, previous lectures. First of all, the point is a point concerning the generalized aerodynamic force matrix. In particular, we are discussing um, the use of this aerodynamic operator in flutter analysis. As we will study next lecture, we will be able to phase these metrics for studying the stability of our flutter system. And we can obtain these aerodynamic metrics as a black box, giving a complex matrix for each value of Laplace variable or frequency. Whenever one has fixed the flight parameter like u in speed, u infinite speed, or the dynamic pressure. Okay, so we have this available for each Laplace variable fixed, and therefore we can't solve numerically this generalized eigenproblem. And these generalized eigenproblems will consist on developing the determinant of this matrix and find the S value satisfying that determinant be zero. We suspended the demonstration about the fact that the free response solution of this system in time will be expressed as a combination of this elementary function like this, where W is the eigenvector and Sn the eigenvector obtained by this problem, and Sn is the eigenvalue. Okay, I have to convince you about the fact that also in this case, for this complicated system, again, the free response is given by this solution structure here. However, supposing that this is demonstrated, then we have to evaluate this pole. And we have two possibilities. The first one is to consider this generalized matrix as given by a black box, and then organize an iterative procedure for finding these poles and this eigenvector in a numerical way. And we will study this kind of approach because this approach is a standard approach in the flutter analysis as performed by commercial codes. Okay, but we have also a second possibility, and we are studying this second possibility in detail, this blue region here. And this second possibility consists of approximating this matrix, which is a function of S, considering as an expansion of this matrix operator as a function of S, and then find the coefficient of this expansion, essentially minimizing the distance between the matrix values given by the computer and this supposed expansion. What about the advantage of this approach? The advantage of the approach is to succeed in describing the system as a standard form linear system. And if we are able to perform this transformation, then we can study the stability in a standard way, just like a standard eigenproblem. So we have past time, the day before yesterday, we have studied this second point here. So supposing to have a polynomial approximation of this matrix as a function of k. So I invite you to distinguish these two parts. In a part, we have the theory we have developed, we have evaluated several factors of this aerodynamic matrix, distinguishing different physical phase, like the development of potential flow, E2 matrix, the Bernoulli theorem, the projection of the force, the boundary condition. So we have decomposed this matrix in a product, and at the end we have a product of this four matrix giving our global aerodynamic force matrix. But after this procedure, this metric will be or should be evaluated numerically by implementing this kind of space discretization process, period. Now we have a code giving us the value of this matrix for each S value, Laplace variable, or for each omega value, the Fourier variable. In particular, we can use undimensional variable like P for Laplace and K for omega for the frequency. Now we have an alternative. The alternative is, okay, evaluate this matrix in a finite number of reduced frequency point, like here, K1, K2, K3, K4, K5. So do a finite number of evaluation of this matrix, each element of this matrix, and on the base of this evaluation, find this interpolating formula for such a matrix. And what about this advantage? The advantage is the following: if we consider this formula or this expansion, evaluating this red matrix A0, A1, A2, on the base of the knowledge of this coefficient matrix, we will represent, going back to the time domain or in the Laplace domain, we represent our aeroelastic system in a standard state space form, which means only differential equation. And now today, I want to convince you on this item, on this advantage, and I want to show you how this may happen. Okay. We in particular propose two kind of interpolating structure. The first one is this number yellow one, this one here, is this kind of interpolation. And in this first part of the interpolation, we have some coefficient unknown, like the red one, and some coefficient, like the blue one, beta here, fixed. And this beta in the denominator has the role of pole of the aerodynamic operator, because these are values such that jk, whenever assume this value, make the denominator equal to 0. So these beta are the structural poles of aerodynamic poles, and these poles beta, beta 1, beta 2, and so on, are fixed on the base of a maximum frequency of the problem. Okay, so if we assume this first interpolating formula, we have this, and we can estimate the error between this formula and the data, and we can minimize the global error of this interpolation, so identifying the red coefficient A0, A1, and A2, asking or requiring that this global scalar error be stationary with respect to the matrix value. And so we have in this other view graph, we have determined this scalar error, and we have imposed to this global scalar error to be stationary with respect to the matrix coefficient. And so we have just imposed that the derivative of this scalar error with respect to each term of this matrix be 0. Since the error is a quadratic function of A, the derivative is a linear expression of the A coefficient, and therefore we have just to solve a linear problem for minimizing the error and so determining the interpolation structure. This kind of approach, I emphasize, be very, very similar to finding linear regression of data. Probably many people know this approach, and this approach consists on first starting by a set of data, x couple x and y couple in this plane. The couple are given by this black point here, and we have this black point, very chaotic, and so demonstrating some linear, potential linear relationship between x and y quantity. So we can suppose to be this relationship linear, and we could find which is the best linear approximation between these two quantities. And how can we do in a very similar way as we have done for the aerodynamic matrix coefficient? We can suppose to have this red linear relationship, excuse me, this linear relationship here, okay? And so the unknown are the m coefficient and the q coefficient, the slope of the straight line m, and q term, which is this value here. So we can assume that the value assumed by the linear straight line, which is this quantity mx data plus q minus the ym data, which is the difference between these two values, this error summed for each couple of number for all the data give us a global error between the black point data and the red line. And we can impose that this error be stationary. Just take it in this case. In this case, we have to take the derivative of, excuse me, I have to organize with my pen. In this case, we have to impose that the derivative with respect to m of the error be 0 and the derivative with respect to q of the error be 0. If we take these two equations of this quantity, which is a quadratic quantity with respect to m and q, which are the unknown, do not forget this, m and q are the unknown, as the red matrix here are the unknown of our aerodynamic matrix. So imposing this derivative of this quadratic expression b0, we will obtain a linear relationship in the quantity m and q in this case. And so we are able to determine the straight line, which is the best straight line fitting the data. Okay. However, after this comment, we have proposed another structure for interpolating our aerodynamic data. We started by this yellow one, number 1, and we proposed the number 2 here, another proposal. And we had this proposal because we realized that the first one was critical on assuming that these beta values are assigned. If we assign some quantity in interpolating structure, we are actually reducing the space for searching the best optimum value interpolating the data. So we would like to have the poles as unknown as well. And therefore, here we have this other proposal, the proposal number 2. And note that in this proposal number 2, the polynomial part are exactly the same. So we have exactly the same polynomial part here, because we know that this part is true, is an interpolating part, but this interpolating part also is corresponding to a physical part that we know that exists, because we know that it exists a quadratic dependency on the square of S. We demonstrated this by our theory, because we realized that we have an aerodynamic max, an aerodynamic damping, and an aerodynamic stiffness. because we have a product of S by S, so maximum and S squared in our theory, remember? And therefore we keep this part and we propose another structure for the other part. And this is something like a matricial fraction. We have a numerator like R by JK, a denominator like this here. Okay? So this is another proposal. And after this proposal, the disadvantage of this proposal is that if you make the same as before, defining an error, blah, 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 you will realize that the global error in this case should be a nonlinear function of the unknown matrix A0, A1, A2, P and R, because we have a P at the denominator representing the poles. Okay? Therefore, we can, however, organize this advantage, just redefining the error in this other way for determining, for defining another error quantity, just multiplying the error expression, which is this here. This is the error expression. We have the data, computer data, minus the interpolated graph. So the error is the difference between the data and the interpolated data. Okay, but we don't want to work on this error, because in this error structure we have this blue quantity at the denominator, and so we will not consider this error, but we will consider this error multiplied by this quantity, which is the denominator itself. And therefore the new error is the old error but multiplied by this function. So we have the old way, something like the old error just weighted with a weighting part composed by the denominator. And therefore this is the new local error. It's local because this error is an error matrix depending on frequency. And in order to obtain a scalar, remember that when you are optimizing in your life any kind of thing, you are obliged to have a scalar quantity. Only a scalar quantity can be optimized. Remember, never a vectorial or a matricial one. So we have to obtain a scalar error. So taking my new matrix error and then summing the matrix error for any frequency and any element of the matrix. And at the end, we have a stationary, we have a quantity depending on the unknown matrix. These are the new unknown matrix, A0, A1, A2, and PR. And then we can evaluate, imposing again the minimum with respect to this. So we have, this is the new approach. And this new approach, number 2, we can obtain as a minimum value the value of the matrix A0, A1, A2, but also P and R. Okay, let me recap. Now, recap the use of so-called finite state approximation for the generalized aerodynamic force matrix A for flutter analysis. So we can assume this approximation 1, like A0 plus A1 JK plus A2 jk to the power 2 plus summation of m from 1 to number of poles of jk by a m plus 2 divided by jk minus beta m. This is the first one, but we have as alternative this approximation 2, another kind, a0 plus a1 jk plus a2 jk to the power 2 plus, and here we have the structure jk identity minus poles matrix to minus 1 by R matrix jk. And these are the two structures, and in the applied in the industry, this is also known as Roger approximation. Roger is a guy by Boeing that in the 1718 introduced this kind of approximation, Roger approximation. And there are also some names in this second approximation, but there are several different names associated with this kind of approximation. I want to do a comment on this. We have a complex plane, and we have, in general, a matrix with element function of this complex variable plane. We have the real part, and we have the imaginary part of the Laplace variable, and we have a matrix of function of this complex domain. Or please, I prefer to use the undimensional domain, so use P instead of S, okay? P is Laplace variable by the length divided by u infinite. Okay, so we have a function depending by complex variable P, and here we have the real part and the imaginary part of P, okay? Now we have evaluated this function in a number of discretized value of P frequency. So this is K1, K2, K3 value, just this value here. We have evaluated the aerodynamic matrix in finite number of reduced frequency value, and the reduced frequency is the imaginary part of P. Okay, so we have evaluated this function here. Note that this is a complex function. Next, we have interpolated this value, and we have obtained interpolated form of this function on this axis, in this axis which is the imaginary axis. So we have worked on the imaginary axis, okay? And this imaginary axis we have interpolated E as a function of K, which is the reduced complex variable in the imaginary axis only. And these are the approximation. These are the approximation. The analytic approximation we have obtained are the following: are this A function of K and this A function of K. Just here, this blue line. Now there is an important theorem of the theory of a complex number. If you know a function a complex valued function. Complex valued function in Italian is una funzione a valore complesso, Quindi il codominio è complesso e il dominio pure è complesso. Ok, so if you have a known, if you know a complex valid function of a complex variable, so if you know a function mapping C into C, okay, and if you know, this is the case of E function of P in our cases, and you know analytically this function in a continuous subdomain of P, and this is our case because we know the interpreted function in this straight line in the imaginary axis. So we know we have determined our function in this line. Then you can expand the function definition in all the domain in all the complex domain by substituting jk equal to p. And therefore, from your E interpolated one function of k, you can obtain your E interpolated function of p. This could be a very, very formal step for an engineering. Yes, maybe it could be. But this is not so obvious. We have determined our frequency domain interpreted function. We have worked on the Fourier domain, on the reduced frequency domain. We have evaluated our function in the frequency domain axis. And we have interpolated our aerodynamic matrix data in the frequency domain. So determining our coefficient matrix A0, A1, or P and Q and so on. Okay. And now our step is the following. We want to move from this to this P approximation 1, which is A0, okay, plus A1, okay, by P plus A2 by P squared plus in the first form we have AM plus 2, and we have P divided by P minus beta. And in this other form, in the second one, we have the approximation 2 P. We have A0 again plus A1 P plus A2 P squared, and finally we have the new fractionary form IP minus I P minus capital P matrix minus 1 R P. Okay? So we have essentially correctly expanded the domain of the definition. In this way, I can work on this interpolated form also in the Laplace domain, besides the Fourier domain as well. So we have performed an expansion of domain from Fourier to Laplace. And now I'm ready to enjoy the advantages of such approximation. For the generalized aerodynamic force matrix. We have our flutter equation. We have our elastic system. Our elastic system is composed by structure, aerodynamic, and then we have a feedback with the aerodynamic here, and this system with this feedback is described here by the following equation in Laplace domain. And we have equal to dynamic pressure by E, function of S and U infinite, and this is applied to, to the state space variable, and this is equal to this applied to the state space variable as well. And eventually we have here external force, if any. These are the external force. F external, F external. Okay, we want to use an interpolated form for this part now. Okay, and then let me take the advantage of this in Laplace domain. Please use the second approximation, consider the second approximation, and rewrite our system in this form. We have a square m plus k. Of course, remember that our physical displacement is equal to the expansion of our modes combined with our generalized variable here. So this is the connection with the physics by our Lagrange equation of motion, always, okay? So we have this applied to Q are modal coordinate, not physical. I am avoiding to use the bar over Q in order, for the sake of clearness for the notation, okay? But we are considering modal in general, modal coordinate, modal Lagrangian variable. Okay, so we have the structural part, and here we have a feedback indicated here in this way. And now we want to express dynamic pressure, our aerodynamic matrix in this form. And therefore we have H0, let H0, excuse me, H0 plus A1 by P. But remember that P, this P here, is S by a reference length. L is typically a reference length equal to the half chord as standard choice in aeroelasticity, the half chord of the airfoil, of the average chord if you have an aircraft with a swept wing or with a different value of the chord along the wingspan. And so we have A1 by S by L divided by U infinite plus A2, we have S square L square by U infinite square, and here we have plus S L by U infinite identity matrix minus P matrix minus 1 R SL by U infinite. And this is applied to the state space vector, the model coordinate vector, plus F external. Okay, so we have remember that all these metrics are evaluated by the aerodynamic analysis and step 2, the interpolation process on the aerodynamic data. Okay, known by aerodynamic analysis plus interpolation. Interpolation in the frequency domain and then an expansion of Laplace domain. Okay, now we have just to recast our system in a suitable form, and I want to first consider here the fact that I want to have your attention in this point, which is a very interesting point, and probably you face this point in your control systems, in your control system course. We have a fraction as a function of S with a denominator of degree 1 and a denominator of degree 1. Look, you have here you have S at the numerator, and here you have S at the denominator, because here you have to the minus 1. So the point is the following: when you have a scalar quantity and you have S by S minus P, you can do the polynomial division, and you have 1 minus S plus P 0 P, and so the result of this division is 1 equal to 1 plus you have P, as you have P, right, divided by S minus P. Okay, so this is the result of the division and this is your rest. Okay, unfortunately we have a matrix division. Oh wow, oops. What can we do? In particular, we have SL divided by U infinite by E minus P to the minus 1. This is the denominator. And we have a numerator like R SL by U infinite. Okay. If what I say, my statement is the following: this quantity, which is a division like this, similar, this quantity is equal to this value, which is a matrix, which is the result of the division, plus the rest, which is P in our case. The rest is this. And now we have as a rest the quantity P matrix by R. And here we have the denominator as well. We have SL by U infinite by I minus P to the minus 1. So look, we have an interesting, quite straightforward parallel between the scalar concept of division and the matrix concept of division. So this division, matrix division of this polynomial matrix function of S is equal to this quantity plus this quantity. How can we demonstrate this? It's very easy to demonstrate, because to demonstrate this, just pre-multiply this by the quantity SL U infinite I minus P. In fact, if you pre-multiply both terms of this, I am talking about this result, if you pre-multiply by this factor, you have R as by matrix SL divided by U infinite is equal to pre-multiply, excuse me, and so you have SL divided by infinite I minus P by R plus PR. And so we have R SL by U infinite equal to SL U infinite by R, and then PR. This is obvious, of course, but it's just to convince you on the fact that we can do a division also between matrices, but we have just to be careful on consider that for matrix multiplication and then also for the division, we have to be very careful with the order of the multiplication, the order of the matrix in the multiplication process. So after this discussion, we can transform this part here. We can transform this part here, just performing the division, and we can rewrite here our equation in the following form. We have a square m plus k q tilde equal to dynamic pressure. Dynamic pressure, remember, is QD, dynamic pressure, And then we have S square L by U infinite A2 plus SL U infinite A1 plus A0. And then now we can use this division process and we can write this here. Instead of the original quantity. And we have R, excuse me, we have R plus SL by U infinite identity minus P to the power minus 1 PR matrix, and finished multiplied by Q tilde plus eventually our external force. Okay. Note that now here we have a proper fraction. Proper means that the degree of the numerator is lower with respect to the degree of the denominator. The degree of the S power, of course. I'm talking about S or P value, which is the same. Okay, so we have now a proper fraction. Proper with respect to S power, and we are happy for this. And this is the result of the R is the result of the division, of the matrix division. I want to take a break, and now I am really ready for going back to the time domain and show to you that now we have a state space form for our elastic system with a set of ordinary differential equations. Okay, let's have a break.